Model checking is an automated verification technique that allows us to check whether a system model satisfies a desired property. Imagine you have designed a complex system, like a computer program or a digital circuit. You want to make sure that it always behaves correctly, no matter what inputs it receives or what environment it operates in. Instead of manually testing every possible scenario, which can be very time-consuming and error-prone, model checking provides a formal and systematic way to verify the system's correctness. We start by creating a mathematical model of the system, which captures its essential behavior and properties. This model represents the system's possible states and the transitions between them. Then, we specify the desired property that we want to verify using a formal language called temporal logic. Temporal logic allows us to express properties that involve time, such as always, eventually, or until. Finally, we use a model checker, a software tool that automatically explores all possible executions of the system model and checks if the desired property holds in every possible scenario. If the property holds, the model checker confirms that the system satisfies the desired behavior. CTL model checking is a specific type of model checking that uses computation tree logic, or CTL, as the temporal logic for specifying properties. CTL is a powerful logic that allows us to express a wide range of properties, focusing on branching time. Branching time considers all possible future executions of the system from a given state. In CTL, we can use operators like always, AG, eventually, AF, until AU, and exists a path, E, to express properties about the system's behavior over time. For example, we can specify properties like the system will always eventually reach a safe state, or it is possible for the system to reach an error state. The model checking algorithm for CTL systematically explores the state space of the system model, checking if the specified CTL property holds in each state. It uses techniques like graph traversal and fixed-point computations to efficiently explore all possible paths and determine the truth value of the property. CTL model checking is a crucial technique in formal verification and has numerous applications in various fields. It provides a rigorous and automated way to ensure the correctness and reliability of complex systems. By formally verifying system properties, we can detect and eliminate design errors early in the development cycle, reducing the risk of costly bugs and system failures. In safety-critical systems, such as aircraft control systems and medical devices, CTL model checking is essential to guarantee that the system operates safely and reliably under all circumstances. It helps identify potential hazards and ensures that the system meets stringent safety standards. Moreover, CTL model checking is valuable in hardware and software design, communication protocol verification, and security analysis. It allows engineers and researchers to verify complex designs, detect potential vulnerabilities, and build more robust and dependable systems. Let's consider a simplified example of a traffic light system to illustrate CTL model checking. Imagine a traffic light with two states, red and green. The system transitions between these states based on a timer. We can model this system using a state transition diagram where each state represents a possible configuration of the traffic light. The transitions indicate how the system can move from one state to another. Now, let's say we want to verify the property. The traffic light will always eventually turn green. We can express this property in CTL as AGAF green. This formula states that for all paths, A, globally, G, it is always true that eventually, AF, the system will be in the green state. A CTL model checker can automatically verify this property by exploring all possible paths in the state transition diagram. It would confirm that from any state, there is always a path that eventually leads to the green state satisfying the specified property. Section 5. Temporal Logic and CTL. Temporal logic plays a crucial role in CTL model checking by providing a formal language to express properties about the system's behavior over time. Unlike propositional logic, which deals with static truth values, temporal logic allows us to reason about propositions that change over time. CTL, or computation tree logic, is, well, a specific type of temporal logic that focuses on branching time. It assumes that at each moment, time can branch into multiple possible futures. CTL provides operators that allow us to quantify over these possible futures and express properties that hold along all paths or some paths starting from a given state. CTL formulas are constructed using atomic propositions, logical connectives like AND, OR, and NOT, and temporal operators. The temporal operators in CTL include always, denoted as AG, a property holds in all states on all paths starting from the current state. Eventually, denoted as AFA, property will eventually hold in some state on all paths starting from the current state, until, denoted as AU, a property holds until another property holds on all paths starting from the current state, and exists a path, denoted as E, there exists at least one path starting from the current state where the property holds. Section 6. Theoretical challenges in CTL model checking. While CTL model checking is a powerful technique, it faces theoretical and practical challenges. One major challenge is the state explosion problem. As the size and complexity of the system model increase, the number of states can grow exponentially, making it computationally infeasible to explore the entire state space. Another challenge is the expressiveness of CTL. While CTL can express many important properties, there are limitations to its expressiveness. Some properties, such as those involving fairness or liveness under fairness constraints, cannot be easily expressed in CTL. Researchers are actively working on techniques to mitigate these challenges. Symbolic model checking, for example, uses symbolic representations of states and transitions to handle larger state spaces. Other approaches include partial model checking, abstraction techniques, and compositional reasoning. Section 7. Algorithms for CTL model checking. CTL model checking algorithms systematically explore the state space of the system model to determine the truth value of a CTL formula. The basic idea is to compute the set of states that satisfy the formula recursively, starting from the atomic propositions and working up to the top-level operators. One common algorithm is the labeling algorithm, which assigns labels to states based on the subformulas they satisfy. The algorithm starts by labeling states that satisfy atomic propositions and then propagates labels upward based on the CTL operators. For example, to check the formula AGP, the algorithm first labels all states where P is true. Then, it iteratively labels states that have all their successors labeled with AGP. This process continues until no new states can be labeled. The states labeled with AGP at the end are the ones that satisfy the formula. Section 8. Another example. Verifying a simple system. Let's consider another example to reinforce our understanding of CTL model checking. Imagine a simple system with three states: idle, working, and error. The system starts in the idle state and can transition to the working state upon receiving a request. From the working state, the system can either successfully complete the request and return to the idle state, or encounter an error and transition to the error state. We want to verify the property. If the system is in the working state, it will eventually return to the idle state. We can express this property in CTL as AG working, AF idle. A CTL model checker would explore the state space and determine that the property holds. From the working state, there is always a path that leads back to the idle state, either directly or through the error state and back to idle. Section 9. Conclusion. CTL model checking is a powerful technique for verifying the correctness and reliability of complex systems. By using temporal logic to express system properties and automated algorithms to explore the state space, we can formally verify whether a system behaves as intended. While CTL model checking faces challenges such as the state explosion problem and limitations in expressiveness, ongoing research continues to improve its scalability and applicability. As systems become increasingly complex, CTL model checking will play an even more critical role in ensuring their safety, reliability, and security.